sign into chat. Sick. Yes, it's me. All right. Can you... Are we... I don't know if we're streaming. Probably. Maybe not.
Check.
Oh, it says we're live. That's cool.
Cool.
All right. Sweet. Yeah, it's a little... All right. Can you... Are we... I don't know if we're streaming. Probably. Maybe not. Okay, great. I could send this to Kelly. That might be funny.
Okay, yeah, cool. I can hear myself, too.
Sweet. All right. We got it all working. I'm going to send this to Kelly because she'll get a kick out of it. Interesting. It says upcoming, but scheduled for 12/27, 4/24. But that's right now. Excuse me. All right. If it works, it works, and if it doesn't, it's fine. All right, cool. So the point, we're here. Last time we talked about Gaussian elimination, right? All right. So you can hear me, right?
Yeah, I can hear you.
Yeah, cool. All right, cool. So today the goal is to talk about... Ooh, I wish I could see very easily like how zoomed in I am. So today we're going to talk about matrix multiplication. Okay. Get my iPad. Okay. All right. So before we kind of talked about x plus y plus z equals 2 and 2x minus 3y plus 6z equals 8 and 3x minus 7y plus 5z equals 10. And we said that we could write the augmented matrix for this, and that would be 1, 1, 1, 2, 2, negative 3, 6, 8, 3, negative 7, 5, 10. And we used Gaussian elimination to get it in the form, 1 something something 1 something 0 0 1 something 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 with this staircase-like thing, right? And we used our row operations, which were that we could interchange any row, right? Just kind of like we could interchange any equation. And we can scale any row. Just like we could multiply both sides of the equation by any non-zero number, right? And then we could add rows. So we could do something like R1 plus R2 into R1. And using these row operations, we could get this form, which we called echelon form. And then once we did that, we were able to do like z equals 2. This is called back substitution. Y plus 2 making up a number equals 8, right? Y equals 6. And then same thing for x. Okay. So what we're going to learn next, we're going to kind of take a break from solving systems of equations and learning a little bit more about matrices. Okay. So a matrix, hold on. Okay. A matrix is a set of rows and columns, right? And usually we denote matrices with capital letters so that we know that we're talking about capital letters. So we'd say something like A, capital A, equals this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'd say that this has 3 rows and 3 columns. So we'd call this a 3 by 3 matrix. So more generally, people tend to call these like M by N because we could have any number of rows and any number of columns. And this is something that you'll use a lot if you take like a neural networks class, where they do a lot of work with matrices that are really, really, really big, hundreds or thousands even of rows and columns. But we keep it simple. So some basic operations, like let's say that I had a matrix A equals 0, 1. This is a 2 by 1 matrix. Mm-hmm. And I wanted to add this matrix to another one. That was like 3, 2. This works because they are the same dimensions. So we can just add these by doing the first row plus the second row. Cool?
Cool.
All right. And we can multiply a matrix or a vector by some scalar. And so we would do that by, say, like 3 times 2, 4. And we could just multiply 3 into both of these numbers and get 6, 12. And that works too. Mm-hmm. Now, if you want to multiply two matrices, so like let's say I have A equals 0, 1, 2, 3, and B equals 4, 5, 6, 7. This you can also do. Okay. But you can only do this. You write this as A, B. Right. You can only do this if the number of columns in A is the same as the number of rows in B. So because these are both 2 by 2, and this is equal to this will work. But if I had a different matrix, one moment, 0, 1, 2, 3, because this is 2 by 2 times a 3 by 3, and 2 is not equal to 3, you're not allowed to do this. Okay?
Mm-hmm.
Okay. If you want to multiply two matrices together, A equals 0, 1, 2, 3, and B equals 2, 3, 4, 5. The way that you do this is you'll end up with a matrix with the same number of rows as A and the same number of columns as B. Right, so this is also going to be a 2 by 2.
Mm-hmm.
And if I had, let's say this was a 2 by 3, these are the same, so this will work, and you'll end up with a 2 by 3. Oh, you can't see here, like this. If I took out this extra row, now I can do this.
Mm-hmm.
Okay. Okay. So if I want to do this, I'm going to end up with just kind of be illustrative here. This is kind of what you would do. So you would take the first row in A. Let me scroll up. That's 0, 1. And you would multiply this by the first column in B. So you're taking the rows in A and multiplying them by the columns in B. Okay, looks like this. And I'll show you how to simplify this in a second. So now the first item is the first row in A times the first column in B. And then the second item is the first row in A times the second column in B. And then down here we have the second column in A times the second row in A times the first column in B. And then here we have the second row in A times the second column in B. Okay?
Yeah.
All right. Now, when I have a 1 by 2 times a, this is a 1 by 2, and then this is a 2 by 1. We're going to end up with a 1 by 1, which is also just a scalar. Right? So this is just going to be a number. Because we're just going to end up with an entry that has one row and one column, which is the same thing as just a number. Right? So 0, 1 times 2, 4 is just 2 times 0 plus 1 times 4. 0 plus 4 equals 4. Okay, so if I go down here, our first entry is going to be 4. Make sense so far?
Yeah.
Okay, great. And we'll just do it out. So what would this next one be? We have 0, 1 times 3, 5.
You'd want to do 3 times 0 plus 1 times 5.
Cool. And then the next one, 2, 3 times 2, 4.
And then 2 times 2 plus 4 times 3.
All right, and then finally, last one.
Then we do 2 times 3 plus 3 times 5.
Excuse me. Cool. And that's how you do it.
Sweet.
Cool. All right, let's pick up a practice problem. All right. Just taking a screenshot of this. All right, let's do a couple more of these. All right, so number 1.
So we'd want to start with multiplying the first row of matrix A with the first column of matrix B. So we do 0 times 6 plus 2 times 3.
All right. And then why don't we simplify this? Make this a little lighter. And then what's next? We can simplify afterwards.
We would do 2. Would we do 2 times 6 plus 2 times 3?
So we're gonna
Would
do
be,
this one
or we're just like you
next.
want me to finish this one?
What I'm thinking is we'll do like write out everything and then we'll write the
Yeah.
final matrix. Okay.
Okay.
So what's the first column? First row, second column of this matrix.
So we do 0 times -6, right?
Mm-hmm.
Plus 2 times 0.
Mm-hmm. And then the
And then we
second row,
do
first column.
-2 times 6 plus -5 times 3.
Mm-hmm.
And then -2 times -6 plus -5 times 0.
Cool. And then simplifying that out would just be 6, 0. -2 times 6 is -12 plus -15 is -27. And then -2 times -6 is +12 plus 0. There you go. And then how about this one?
Number 6?
Number
Which
2.
one is your mouse over? Number 2.
Number 2.
This one's only going to be 1 by 1.
Mm-hmm. That's right.
So we're going to do just 6 times -5 plus -3 times 4.
That's right.
So -42.
Yep. All right. So I think you're getting the hang of it.
Yeah.
Why don't we just do from here, like, let's just check, like, can we do this? Right?
Yeah.
All right. So this is, what kind of matrix is this? Number 3 here. Like, how many rows and how many columns for each one?
2 and 2.
Mm-hmm.
So we can do that one.
That's right.
The amount of rows in the first one is equal to the amount of columns in the second one. Or is it back? Did I say it backwards?
It's backwards, yeah. So it's columns
Okay,
in
yeah.
A times rows in B. Or sorry, columns in A need to match rows in B. Okay. And how about this one? Can we do this one? Number 4?
Yep, same thing.
All right. How about number 5?
This one's going to be no.
So this one is a 3 by 2
Mm-hmm.
times a 2 by 2.
Oh, yeah.
So we can do this one. All right. How about number 6?
I suppose the same thing, just reversed.
So this is what, 2 by 3
Mm.
times a 3 by 2. Looks good. This is a 1 by 1. And how about number 8?
Number 8 is not 2 by 3.
Oh, I made a mistake here. So this is 2 by 3 times 2 by 3.
2 by 3.
So can we do this one?
Can't do it.
No. Okay, great. So I think you're getting it. Let me see if there's a more complicated one, something I can show you. I think this reviewing this is just like pretty basic, I think.
Yeah.
You'll do this in your like intro to linear algebra. And you'll end up just doing a lot of this stuff in your head eventually.
Yeah.
All right. Let's see the next thing I can show you. Okay. So kind of going back a little bit to systems of equations. Let me find my worksheet. Hold on, I have it. Saved off. All right. All right. So this was one that I did for a quiz. It was 2x minus 3y equals -5. So 2x minus 3y equals -5. Okay. And x plus y equals 5. All right. So I don't know if we've been over this, but there were kind of two different ways to think about this system in ways that we could graph. And I don't remember if we talked about this, so we can go over it either way.
Yes.
So the first way of thinking about this is what we'll call the row interpretation. Okay. And in the row interpretation, we can think about solving this. This is pretty much what we did in like Algebra 1 and 2, where we can think of these systems as lines on a graph in the XYZ, or sorry, in the XY plane. And we can think of the solution to these systems as the point where the two lines cross. So with the row interpretation, we could think about this as y equals 2x over 3 plus 5 over 3, right? And we could think of this one as y equals 5 minus x. And then we could graph these. 1, 2, 3, 4, 5. This is the point 0, 5. and 1, 2, 3, 4, 5. This is the point 5, 0. And then we could do, let's pick 2 points that, well, I don't know if it's going to be, excuse me, an easy way. I guess if we did x equals 2, then y, let's call this y1 and y2. All right. So this one is easy to graph. This is y1 equals 5 minus x. And then y2, where x is 2, just to pick 2 points that work well, would be 2 times 2 over 3 plus 5 over 3 equals 4 over 3 plus 5 over 3 equals 3. All right, so we have a point 2, 3 on this line. 1, 2, 1, 2, 3. And just thinking of one that also works, I guess if we did minus let's just put 5 over 3 here. So 5 over 3, so 0, 5 over 3 would be like just under 2. And then we would graph this. And it just so happens that we found this. So this is like pretty simple because the row interpretation is just exactly what we've done before, right? All right, let me move this somewhere else. All right. Now, the column interpretation of this system would be thinking about this system of equations as a vector equation. And the way we would write that is it's this very similar. So we have x and y, and then this is equal to something. And then we're essentially going to multiply x by a vector and multiply y by a vector, and then that's going to equal some vector. And the way we would write this is like this. So we're multiplying x and y by vectors, and then that's going to get us a vector. And the vectors here would just be the coefficients. So we have 2, 1, and we have -3, 1. And then this is equal to -5, 5. Right? So if we graph this, the idea would be we're trying to get to this point, -5, 5. And the question is, how could we multiply these, how could we add these two vectors in a way that brings us to this point? right? So the way that the vectors would look is we have let's take 2, 1 is this vector, right? So the idea is we need some way, let's say we had like 2, 1 plus 2, 1 plus 2, 1, and then maybe we want to add the other one a little bit, -3, 1, -3, 1, something like this. Is there a way that we can add these vectors up so that we end up landing at this point? So let's start with just drawing a vector. So we can start with x, right? The x vector here. So maybe let's call this A. Trying to, my Apple Pen is not, oh, I got the eraser going. All right, so we can say like A equals 2, 1, and B equals -3, 1. And this little arrow here just means that we're talking about vectors. Okay. So let's start with just putting on the graph A and B by themselves. So the A vector we could draw by just, all these vectors are going to go through, like if you're just, where basically the vector is you could start at any point, and then the A would be, you would move over to the right 2, so 2 in the x direction, and then y in the 1. Because the vector you can kind of start from any point and then add the vector to that, right? So if we had like 0, 0 as the origin, right? And then we added 2, 1. This would just take us to 2, 1, right? So we can just draw that. 2, 1. And this is A. And then if we did the same thing with B, we could go from 0, 0, and then add -3. Let me zoom out a little bit here. We could add -3, 1, and we would end up at -3, 1. So that would be 1, 2, 3, 1. And then this would be B. Okay. Now we can go from any point and add the next vector, right? So we can go from 0, 0, and then add B, and then add A. Right? And so if we did that, we'd go from 0, 0, and then we would add -3, 1. And then we could add 2, 1. And the way that would look is we would start at where B ends here, and then 1, 2, 1, and we would end up here. Right? And so the goal is, can I add these vectors in a way where we end up landing on -5, 5, right? So if right now we're at -1, 1, and we want to end up at -5, 5, then we're going to need to go further back in the x direction and further up in the y direction. So adding either A or B moves us 1 up in the y direction, right? But the only way that we're going to get further back in the x direction is if we add more B, right? So we could add another B here. And if we went from, let's see, so 0, 0, excuse me, plus b plus a plus b again. This would be, well, we're essentially going from negative 1, 1, and we're adding another negative 3, 1. That's going to bring us to negative 4, 2. Right? So we can go up here and add another b. So we're going 1, 2, 3, 4. Did I make a mistake here? Yeah, I made a mistake here. So this is negative 1, 2. So we're going from negative 1, 2, adding negative 3, 1. We're going to negative 4, 3. Okay. 1, 2, 3, 4, 3. Okay. That's another b here. This is negative 4, 3. Okay. So now we're at negative 4, 3, and we need to get to negative 5, 5. We know that each vector brings us 1 up, so we're going to have to add 2 more vectors, presumably, to get up to 5, right? Because there's no way to come back down if we get above 5, right? Because each of these vectors bring us 1 up in the y direction. So we're going to need to do this in 2 more vectors, right? But we need to get more negative. But if we add another negative 3, 1, that's going to bring us too far, right? Because we're going to end up at negative 7, 4.
Yeah.
Right? But we can add 2, 1 to bring us from negative 7, 4 to negative 5, 5. So if we draw that, we would end up doing 0, 0 plus b plus a plus b plus b plus a. Right? And this would be 0. Let me get rid of this. So we already did a lot of this, so we're going from negative 4, 3, and then we're adding another b, and we're adding another a. So negative 4, 3 plus negative 3, 1 plus 2, 1. This gives us negative 7, 4 plus 2, 1, 5, 5. Negative 5, 5.
Cool.
Yep. So then we do 1, 2, this is 4, 5, 6, 7. B, and then we get an A here. All right. So what we're saying is we can get there if we do B plus A plus B plus B plus A. This is a solution. So that's the same as saying 2A, right, plus 3B equals negative 5, 5. And remember that we had XA plus YB equals negative 5, 5. So that means that x equals 2 and y equals 3. And it's just another way of solving this equation.
Yeah. Cool.
All right, great. The other thing that we haven't really talked about so far that we've gone over in my class is what happens. Remember I told you that if there weren't enough equations that like we couldn't like solve it.
Yeah.
So there are scenarios where we can solve it. and we end up with kind of two, like, infinite solutions. So we say in this like linear algebra that a system of equations either has no solution, right? And in the row interpretation, you can imagine this as the lines never cross, right? So if we had if we just had play pretend here, and we had two lines that were parallel, we know that these lines will never cross.
Yeah.
And so in this case, there's no solution. In the column interpretation, that would just mean we have two vectors that only take us in one direction. Like maybe we have a vector 2, 1, and then we have a vector 4, 2, right? So 4, 2, like we can get to the same place with 1, 4, 2 as we can with 2, 2, 1s, right? And so that would be fine if our constant over here, like the negative 5, 5, if it was on that line, right, then that would be fine. We would end up having a solution. But there'd be a lot of cases where the point is somewhere else, and our vector is only going to take us in one direction.
Yeah.
And so we would never get there. And so in these cases, that's the no solution, right? We're more familiar with the unique solution. It can either be 1, no solution, 2, a unique solution. That's like what we've been talking about, where there's one value for x and y, or there's one value for x, y, and z that brings us to, it converges on one solution. There's only those values work out in all of the equations, right? And it's the same as, if I have many, many lines here. Or I might have, if I had like more than one line here. This would also have no solution, because although these two lines cross here and these two lines cross here, there's no point where all the lines cross. That would be something that looks like this. Right? This is unique solution. And that's typically like what we're familiar with, right? The other possibility is that there could be infinitely many solutions. So the way to think about this would be if we use like the row interpretation, because it's the most intuitive.
We'll scroll down a tiny bit.
Yes, thank you. Please keep me honest, because I'm working on two screens.
Yeah.
Infinitely many solutions would be like if I have two lines that are the same line, right? So if I had like two lines that are like, you graph them and they're actually the exact same line,
Yeah.
then there's infinitely many solutions, right? Because the lines cross at every point. Or if this were in more than one dimension, right? If this were in 2 dimensions, you could also think of it, you end up looking at things in terms of planes, right? So if you have like x, y, z, right? X, y, z. Usually you end up graphing these with planes, right? And so in XY, there's infinitely many solutions if there's the same 2 lines.
Yeah.
In XYZ, it could be that the planes are exactly the same, or it could be that the planes cross and form a line somewhere, right? Like if there's 3 planes, sometimes these 3 planes all intersect at a line, and sometimes the 3 planes intersect at one point. So when they intersect at a line, that's infinitely many solutions, and when they intersect at a point, that's unique solution.
Yeah.
And so these two, unique and infinitely many, when systems are like that, we call these two consistent. So when the system is consistent, it means that there's some solution, but it could be unique or it could be infinitely many. And when there's no solution, we say that the system is inconsistent. There's no solution. Okay.
Yeah.
So just terminology. So that's some stuff that we went over. All right. So now that we've kind of talked about consistent, we have this concept that there could be infinitely many solutions to a system, right? So I'll show you what to do when there's infinitely many solutions, which we haven't gone over yet. Okay. All right. All right. So we got... I'm going to rate this a little differently than we've done before. So this just means this is just another way of writing the systems. Remember we talked about like augmented matrix was like the coefficients and stuff. So A here just represents a matrix of all of the coefficients of the variables, right? Okay. So in X, Y, Z. So here A in this problem, excuse me. In this problem, A is equal to 1, 2, 0, negative 1. 2, 5, negative 2, 0. 0, negative 2, 1, negative 1. And B is equal to 4, 13, negative 4. So this is like saying, another way to write this would be, here X would be like X, Y, Z, W, something like this. Sometimes when it's big, they just write it as like X1, X2, X3, X4. So it's just saying that there's 4 unknowns here.
Yeah.
And we know there's 4 unknowns because there's 4 columns in A. Right? So the augmented matrix here would look like this. 13, 4, 4, 13, negative 4, 2, 5, negative 2, 0, 0, negative 2, 1, negative 1. And so in the more traditional way we think about it, we'd say like x1 plus 2x2 plus 0x3 minus x4 equals 4 would be like the first row in the augmented matrix here.
Yeah.
Okay. So we can solve this using the systems that we worked with before, the Gaussian elimination, using the augmented matrix. And I'll just tell you ahead of time that there's going to be infinitely many solutions here. So it's always going to be when you have like more um, columns than you have rows in the augmented matrix, that means that it's always going to be either no solution or infinitely many solutions.
Okay.
Okay. So we do the exact same process like we did before, but because there's 4 columns, we're not going to get the full staircase. There's going to
Gotcha.
be one column in the end that like we don't have the staircase for. Okay? But it's the process with the row operations is exactly the same. So why don't we practice that? So what would be your first row operation that you would do to get it in the echelon form?
Wait, so can you draw where the staircase should be?
Yeah. So the staircase should look like this.
Okay.
Okay. And we don't have anything here to do the final staircase. Right?
Yeah.
So we're just going to have this column will end up being full of values.
Mm-hmm. Okay, so if we want to turn that 2 in the first column in the second row into a 0, we'd probably want to multiply row 1 by 2, and then subtract it from row 2. So we'd have, yeah. And then we'd get 0 where that 2 is, and we'd get 1.
Yep.
Negative, is that a negative 2?
It's a negative 2, yeah.
Yeah. Negative 2 again. Or sorry. Wait.
So it'd be 0 minus negative 2 times negative 1.
Oh, my bad. So 2.
It would be 0 minus 2 times negative 1. Yeah, 2. You got it. Great.
And then 13 minus 8, so 5.
Yep. And then down here it's the same. Looks good. All right. What's next?
If turn that negative 2 in the second column, third row, into 0.
Right.
So I don't know. Probably just add it. No, I can't do that.
Well, add what? You're on the right track. We have the right idea here. So we're gonna update R3 with some multiple of some value, so that we get, when we add it, we'll get 0. So we need to add 2 to negative 2 to get 0, and we can do that. There's like one way to do it where we don't end up with where we don't like make it more complicated.
Yeah, because we don't want to turn the 1 in the bottom left corner, or sorry, the 0 in the bottom left corner into
right.
a 1.
So we don't want to use row 1, right? Because that'll add 1 in the x1 column. We don't want that.
So I suppose we can just multiply row 2 by 2. And then subtract it from, wait, just add it to?
Yeah, that's right.
Row, yeah,
because then we'll get 2 for row 2, add it to negative 2 in row 3, and we get 0. So that's right. All right, so give me a second to write this out, and then I'll ask you what row 3 should be, the new row 3. Okay, so we have 0, and then another 0.
Mm-hmm.
Okay.
And then
what else?
Another... Oh. We'd have -3, right?
So we'd have 2 plus -4, yep, is -3. That's right.
And then -3 again?
Yep. So -1 plus 2 times 2 is 4. What would it be? -1 plus
2 times
2
2.
times
Yeah,
2.
just 3.
Just 3. That's right. Mm-hmm. And then for the
And then we got to do 10 plus -4, so 6.
Yes.
Is that a negative? Okay, yeah,
Yep,
6.
that's right. Mm-hmm. Cool.
We're just gonna turn that -3 into a 1, right?
That's right. So how would we do that?
Probably just divide that whole row by -3.
That's right.
Or, times, yeah.
Yeah, it's the
1/3.
same. It's just easier to write it this way. Okay. But it's the same thing. All right. 1, 2, 0, -1, 4, 0, 1, -2, 2, 5. 0, 0, 1. What would then what are the other ones be?
-1.
Mm-hmm.
And then -2.
Yes. Okay, great. So now we have the staircase, right? So there's nothing left to do in terms of row operations. Like, we've made it as simple as we can.
Mm-hmm.
Right? So when we have it in this form, where it's got the staircase and it's got a 1 in each column, like the same column as the row, right? We call these columns pivots. Okay? So this is a pivot. This is a pivot. Because it's got the 1. All right? And when we don't have a 1, right? When we just have values, we call this the free variable column. And so in the case where there's infinitely many solutions, there's going to be, some point, right, that's represented by the pivot columns. And then you're going to just scale with the free variable. So if we go back to the idea of the line here, right, when there was many planes and they cross through at a point so that there's a line in between them, right? Do you get what I'm saying? I can pull up a visual.
Yeah, that'd be helpful.
Yeah, let's do that. All right, so planes crossing at a line. That's funny. Here. So, see how these two planes, they're parallel, right?
Mm.
But these two planes, they cross each other like this. So you could imagine if my hand could go through my other hand, these two planes would cross at the entire line of my hand, right?
Mm.
We could pull up more visuals if it's still
That makes sense.
Yeah, like this too, right? Here, and then there's a line where they meet, right? There's also a
Yeah.
way to do it if you had a third plane, where you could slice through the plane, and then they'd all only meet at one point, right?
Mm.
But in this example that I'm showing you, they meet if you think of them like planes, right? Which is you can do that in 3 dimensions, but as you get more and more and more dimensions, it's like impossible to visualize it, right? When you start talking about like a solution that has a vector of 5 variables, right, or 5 values, like it's not
Yeah.
possible to visualize that, but we can with like up to 3 dimensions because like that's the world that we live in.
Mm.
Um, it's possible for them all to meet at a single point, but it's also possible that they meet at a line. Okay. Um, okay. So in this case, you can think of it like there's these planes that meet at a line, right? And the pivot is going to be a point on that line. And then the free variable is going to be like where do we scale through the line? Does that make sense?
Mm.
Yeah. So it's like the pivot will be like this point here. Boom. And then as you add the free variable, it's going to like bring us to another point on the line. Okay. So now we can start to solve it. And so what we need to do, so this first column represents x1. This represents x2, or like y, but you start to run out when you start doing many variables, you run out of letters. So they just do x1, x2, right? This is x3. This is x4, and then this is b. Okay. Hold on. Okay. So that's what each of these columns represents.
Mm.
So that means the x4 is not going to be like part of the solution. It's not going to be on the point, right? There's going to be a 0 there for the point. So the way that you solve this is you just define your free variable. I've seen it used as like t, the letter t. And you can just say, okay, let x4 be equal to t. Okay? Because there's not going to be like if this were fully simple, like if there was an extra row here, there'd be a 1 for x4 and then some value, right? This is pretend, like this, in this case there's only 3 rows, but if there were a 4th row, we could simplify it down such that there was 1 here and then some constant. And then we'd say x4 equals 4, right? And then we would plug x4 into this equation for x right here, because this is you can read this as 0x1 plus 0x2 plus x3 minus x4 equals -2, right? And if we pretend like there was a 4th row here, we could get a value for x4 and then plug it in to this equation and get a value for x3, right? But there's no 4th row. So we're just going to call the like x4 component t. It's some new variable. And then x1, x2, and x3 are going to have like their real solution, their pivot solution, and then their solution that is something to do with t. And it'll be a little more clear when I do the example a little bit further. Is that maybe it'll be easier, right? Like previously when there was one solution, we'd have just a number for every variable. So x1 would be just a number, x2 would be a number, 3 would be a number, and 4 would be a number, right? But now we have this like free variable. So each solution is going to be some constant plus the t part. And so I'll show you what I mean. So I'm going to get rid of this because I made it up and I don't want to get confused. Okay. So this is 0 and this is 0, right? So really it's just x3 equals negative 2 plus x4. But we don't know what x4 is, and we'll never know what x4 is because x4 could be any value, right? So we said that x4 was just going to call that t, just so it's not x, right? And so x3 is equal to negative 2 plus t. And that's the solution for 3. And then we're going to do the back substitution back up for all the other entries, right? So now we have a value for x3. So for our x2 equation, we have x2 minus 2x3 plus 2x4 equals 5. It's clear how I got that?
Not really. I'm kind of losing steam here.
You're losing steam. Okay.
Yeah, like it's getting harder and harder to focus.
Oh, okay.
I'm kind of following you, but
okay. Well, we can be done soon.
okay.
Let me finish this example and then we can.
Yeah.
Okay, great. So this equation I got from this row 2. Okay. So we have a 0 in the x1 column. So there's no x1 component. We have a 1 in the x2 column. So there's 1 x2. Minus 2 x3 plus 2 x4 equals 5. Are you with me? Okay. So now we're going to solve for x2. Because we know x4, we said that was t up here. And we solved x3 is negative 2 plus t. So we're going to substitute in this equation for x3 and this equation for x4 and get a value for x2. Okay. So we're going to say x2 equals 5 plus 2x3, adding it to both sides, minus 2x4. Okay? And then we're going to plug it in. So we have 5 plus 2 times negative 2 plus t, negative 2 plus t, minus 2 times t. And then we can simplify this. So it's 5 minus 4 plus 2t minus 2t. These cancel. In this case, they don't always cancel. Equals 1. So we know x2 is always equal to just 1. And then finally, we're going to do it for x1. And then we're going to get a solution. Okay? Almost done. x1 here plus 2x2 from here plus there's no x3 component, 0, minus x4 equals 4. Okay, so last one. We have x1 equals 4 minus 2x2 plus x4. Just bringing it all to one side. that means x1 is equal to 4 minus, we said x2 is always 1. We calculated that down here.
Mm-hmm.
And we said x4 is always just t. It's just t. So that's plus t. So this is 2 plus t. And so now we're done. We're just going to rewrite it, right? So we said x is x1, x2, x3, and x4, right? X, Y, Z, U, or something. They're just variables, okay? And we said x1 is 2 plus t. x2 is always just 1. x3 is negative, I think it was negative 2 plus t. Negative 2 plus t. And x4 is just t. And so we're just going to pull out the stuff that has to do with t from the stuff that doesn't have anything to do with t. All right? So that would be 2, 1, negative 2, 0. Because x1 has a 2, 1, no t, negative 2, 1 t, and then there's just t here, so it's like 0 plus t, right? So we took the 0. So that's our like real solution, our solution.
Mm-hmm.
And then our like scaled solution, where we're kind of like over the line, is the t value. So we can plug anything in for t and get a value on that line where the planes cross. So we have t times 1. Here we have 1t. Sometimes we'll end up with like 4t, right? And then it would be 4. But in this case, it's just 1 and 0. So we have 1. x2 has no t component, right? There's no t in the x2 solution. So this is going to be 0 for x2.
Yeah.
x3 is 1. And x4 is 1. And this is it. So this is the solution.
Okay.
And then we're done. So I know it's kind of a lot.
Yeah.
But this, when we say infinite solutions, this is what it means, right? We have some point that's like the real solution, where this free variable has no, like, doesn't contribute to it in any way, right? It has 0 for the x4. And then there's infinitely many solutions because we can plug any value in for t. So like we could add, so like this is, just to kind of illustrate what I'm saying here. If we go back to this column interpretation, right? We talked about like 0, 0 plus a bunch of vectors, right?
Yeah.
Well, we have this starting point. We always start from here, right? This is a solution, this one, right? This, if you plugged in 2, 1, negative 2, 0 into these equations up here, like this one, x1 plus 2x2 plus 0x3 minus x4 equals 4, this original, like where we started, if you plug this values in, it would work. And then we can add any number of these vectors forever. We could also subtract any number. You get what I'm saying here?
Yeah.
And it would also solve these equations. That's what infinitely many means, right? I have the point that works, and then I can add this vector to that point, and that will create another solution forever. You could do 1,000 of them, you could do 1,000,000 of them, you can do as many as you want, and you would still get a solution to this system. All right, so you said that you're kind of cooked, so we can end there.
Cool.
If you want, we could. If you want to kind of do your own thing, you could do your own thing, or we could like play a game or something if you wanted.
We could. What is this concept called again? I just want to write it down so I can do some independent research.
Yeah, this is
Yeah, it's a
still
few, sure.
yeah, and I'm just not sure. Like I think this would
Yeah.
still be considered Gaussian elimination,
Mm,
but it would be Gaussian elimination for infinitely many solutions. Let me see if I'm right.
okay.
Elimination for infinite solutions. Free variable. Yeah. So it's still under the umbrella of Gaussian elimination. But if you wanted to learn more, what I would do is search Gaussian elimination free variable. And they'll
Okay.
go over, and maybe they'll do it in another way. I just kind of am regurgitating what my professor taught me.
Yeah.
And maybe they'll do it in a way that's like a little bit more intuitive, and maybe we could talk about it, and maybe it'll help my understanding too. So yeah, feel free.
Yeah.
Cool.
Cool.
Did you want to do something else?
Yeah, I mean, um, I don't know. I was thinking about maybe getting some fresh air,
Oh, that sounds good. I'd be down for a
honestly.
walk.
Yeah.
Yeah.
Yeah, we could do that. That'd be nice.
All right, cool. I'll stop the stream.
Cool.